In today's examples, we're going to keep looking at our special parallelograms with rhombus and square, or rhombi is our plural, and squares. And so don't forget, these are still parallelograms, so they still have all the same properties with all of the opposite sides, parallel, congruent, all the congruent opposite angles. Every single property is the same. The new ones that we're adding in for a rhombus, specifically, all sides are congruent. So it's a parallelogram that instead of just the opposite sides being congruent to each other, they're all congruent to each other. So every single side has the same length. We still have our opposite pairs of parallel sides though. So you might see them marked as this. Then when we start putting in the diagonals in a rhombus, then they do a couple nice things. So let me actually scroll down a little bit. There we go. So anytime you draw in your diagonals, they actually bisect the vertex angles. So that means, for example, the top right angle, the two pieces are congruent. And because those are also going to be congruent to the perfect opposite angles, the bottom left are also cut into the two same pieces. Same thing happens with the other pair of angles. They do get bisected, and the opposite angles have to be congruent. But we still have the same other properties. So if we looked at, for example, this larger angle and this larger angle, putting those together, they still make those consecutive interior or same side interior angles, like what we used in our examples in the last video. The last piece that's important about a rhombus is that when you draw the diagonals, they are actually perpendicular to each other. So that means at the center where your diagonals come together, every single one of those angles in the center is a right angle. So we could, if we wanted to, use all four of those right triangles. And in fact, if you notice with all of the angles labeled and what we know about congruent sides as well, we know that that's actually making four congruent right triangles. So if you know things about one triangle, such as your angles or your side lengths, you know that about all four of the triangles that are made by those diagonals. Alrighty, squares are the most perfect quadrilateral. These are what we think of when we talk about regular polygons. And so being a four-sided regular polygon, it means not only does it have all the sides congruent, just like a rhombus, it also has all corner angles being right angles like a rectangle. So it has all the things of every single parallelogram that's out there. All the properties of rhombus, all the properties of rectangle. So everything in there is created equally. We have our diagonals that bisect each other perfectly, and they're equal to each other, so all the pieces are congruent. We still have 90 degrees in the middle, just like a rhombus. We have all of our congruent sides. So everything is divided up perfectly. In fact, it's even a perfectly symmetric figure in that when you draw your diagonals and the angles get bisected just like they do in a rhombus, then, well, what's bisecting 90 degrees? 45 degrees. So each one of these angles that's cut in half, the half is 45 degrees. So this leads to us being able to use kind of our instinct on a lot more of these problems. So let's look at a few examples. Hopefully the video is not going to be as long as last time because we're not looking at these problems new. We're going to use the same techniques as we did last time, but they're going to be a little bit easier to find, a little bit more symmetric in our shapes. So here we go. Let's start off with some rhombi problems. So example 1, we're given some info. AM, segment AM, is 4x, so let's label that. Let me change over to red so it'll pop better. There we go. And AK is 5k minus 3. We also know that segment DL, the longer segment going all the way across, that whole segment is 10. So I'm going to actually note that down here because it's a little hard to draw on the diagram with the overlaps. However, if I know that that diagonal DL is 10, what does that mean the pieces are? So let's go ahead and label that. That means all the pieces would also have to be 5. So let's go ahead and start looking for things. First thing it wants us to solve for is for x. Now, if I'm looking at my x expressions, the 4x and the 5x minus 3, Well, they're both on pieces of the same diagonal. And if we're using the same idea as the rest of our parallelograms and our rhombus, then how is that diagonal being cut? Perfectly in half. So that means the halves are equal. So 4x equals 5x minus 3. So then all I need to do is combine my like terms. The way I wrote it out though, I don't really want to lose the left-hand side of the equation. So let's actually go ahead and subtract a 5x from both sides. Now it's going to look a little weird because what's 4 minus 5? Negative 1. So I have a negative 1x equals negative 3. But I would still want to get the x completely by itself. So what could I do with that negative 1? Well, negative 1 is multiplying the x, so let's divide both sides by negative 1. And what that does is it lets us find, well, negative 3 divided by negative 1 is positive 3. So we now know our answer for x. So now it's asking us find AL. Well, we already figured that one out. The entire diagonal was 10. If it gets cut in half, half of it is 5. So we know that AL is 5. We already labeled that. Okay, next piece is asking us to find angle KAL. So actually, let me change my color. Let's go to green. So KAL, if I trace that along to see where the angle is, K to A to L, we're actually looking at that central angle. So it's not the 5K minus or 5X minus 3 that was labeling the segment AK. But what do we know about the diagonals in a rhombus? They always intersect at what kind of angle? 90 degrees. So question's actually answered for us. Measure of angle KAL is actually 90 degrees. Any of those angles in the center would be 90 degrees. And so then last piece is to figure out DM. Well, let's think about this a little bit. DM is this segment here. We don't have anything else labeling the rest of our figure. But if I look at this triangle here, what kind of triangle do I know that has to be? Well, it has to be a right triangle because I know all of the angles in the center of this figure are 90 degrees. So if I redraw that triangle, DM is actually going to be the hypotenuse. We have a right angle. One of our segments is labeled as 5 and the other segment is labeled as 4x. And because we already know that x equals 3 from the first part of the problem, I know that that 4x is really going to be 12. 4 times 3 is 12. And so let's go ahead and solve that out. And what can we use to solve for a missing side of a right triangle if we know the other two? Pythagorean theorem. So let's call this C. So I'm not using x just in case. And so we're going to go 5 squared plus 12 squared equals C squared. And actually, before I go any further, anyone notice that combination of numbers, how we could finish that? This is actually one of our Pythagorean triples. Of course, if you don't remember those, you can still do Pythagorean theorem. So 5 squared would give me 25. 12 squared would give me 144. Add those together, I get 169 equals C squared. And so the square root of both sides, square root of 169 gives me 13. So segment DM is equal to 13. And our triple was 5, 12, 13. All right, let's look at the next rhombus problem. We've only got 2 more. Here we go. So let me save so I can scroll. So next problem, let me bump up the size a bit. So next problem, example 2. Given we have rhombus RSTV, we need to figure out segment TV. So segment TV is over here. This is the one we're looking for, but it doesn't have a label. But what do you know about the sides in a rhombus? Every rhombus, the sides are always going to be congruent. So that means that I could label TV as anything I want. I could label it as 5y plus 2, or I could label it as 3y plus 6, or I could just keep in the back of my brain, I know that either one of those would give me my length for TV. And 2, if I know that all the sides are supposed to be equal, what can I do with the expressions 5y plus 2 and 3y plus 6? I can just set them equal and solve that for y. So let's do that. So 5y plus 2 It's a funky looking 5. Let's fix that. Equals 3y plus 6. So I'm going to subtract 3y from both sides, gives me a 2y. I'm going to subtract 2 from both sides, gives me a 4. And so y just equals 2. And so it doesn't matter which one I plug it back into. I'm going to go ahead and use the 5y plus 2 because it's directly opposite. And I know opposite sides have to be congruent in any parallelogram, rectangle, rhombus, or square. So we have 5y plus 2 is really equal to 5 times 2 plus 2, otherwise known as 10 plus 2, or 12. So TV equals 12. Alrighty, example 3. If the figure is a rhombus, find x. So with a rhombus, again, what happens in the vertex? What happens with that vertex angle when we cut it by a diagonal? The pieces are always going to be congruent. So let's go ahead and set them equal. So we have 2x squared equals x plus 3. And it's another one of these problems where we're going to use our factoring that we learned at the end of our factoring mini unit. So again, I want everything on one side of the equal sign. Let's subtract the x and the 3 over to the left to turn it into 2x squared minus x minus 3. And then we have to factor it out. So if we factor out, we have a 2x squared and we have a negative 3. Multiply those. And actually, before I go any further, let me shift this down a bit, give myself a little more room. There we go. Okay, so 2x squared times negative 3 gives me a negative 6x squared. I need to brainstorm on that so I can make that negative x or negative 1x in the middle. And the only way I know how to do that is actually using the positive 2 and the negative 3 that we use to multiply. So if we have a positive 2x and a negative 3x, add those together, we get that negative x for the middle term. So we have a 2x and we have a negative 3x. Common factors in that first column are just an x. In the second column, we don't have any other values in common, so 1 is our common factor. First row, we have a 2x. Second row, they both have a negative 3, and we've taken care of our negative now, so that means the other factor has to be positive. So our factors are 2x minus 3 and x plus 1. And so setting each factor equal to 0, 2x plus or minus 3 equals 0, and x plus 1 equals 0. Add a 3 to both sides, and then divide by 2, so x equals 3 halves. And then in our second one, subtract a 1, so x equals negative 1. And so looking at plugging these back into our expression, again, either one of these would still make a positive value. If we plug into squared, well, anything squared gives us a positive number. If we plug into x plus 3, well, even the negative 1 plus 3 still gives us a positive 2. So both of those are potential answers. So x equals both negative 1 and 3 halves. Again, not as many examples on these because you can still use the same properties as what you were practicing with parallelograms. But keep in mind your diagonals are always going to be congruent and they always cut the corner angles, the vertex angles in half, as well as all of the sides are congruent. Not the pieces of the diagonals, just the sides. So now let's look at a few square examples and then we'll be set for our special parallelograms. Here we go, example 4. So same kind of thing as we saw before, we're going to be given some information and we have to fill in the rest of the pieces. PQRS is a square. So I know all the corner angles are 90, all the sides are congruent, all the pieces of the diagonals are congruent, my corner angles get cut in 45 degrees, and that center piece is all perpendicular. They tell us segment TR is 5. So if that's the case, what else can I label as 5? Well, all the rest of the pieces of the diagonals are 5. Everything's bisected, everything's congruent for a square. Everything is perfectly symmetric on a square. Okay, so let's start filling these in. So segment PR, well, that's an entire diagonal. If the two pieces are 5, then the whole thing needs to be 10. QS, again, it's just another diagonal. QT, we already figured out was 5. Here's a different one though. PQ. So PQ is actually this segment. I don't have a label on that segment, but isn't it part of a right triangle? So let's go ahead and call this guy X. And if I use the right triangle that I have up the top, I have a 5, I have a 5, I have an X. So I can do 5 squared plus 5 squared equals X squared. So then adding or simplifying out, we have a 25 plus 25 equals X squared, otherwise known as 50 equals X squared. And I can express this actually in two ways. When I take the square root of X, I'll get the square root of 50. Now I can do this two ways. If you remember how to simplify radicals from Algebra 1, and we talked a little bit about this when we did distance formula, then all we do is say, well, 50, that's the same thing as my perfect square of 25 times 2, which I can simplify out to 5 root 2. Or I could do the decimal version of this and plug it in my calculator. Square root of 50 comes out to be approximately 7.07. So either one of those would be appropriate. Again, a lot of problems in multiple choice, you might see that we have that reduced radical version. But if you just plug that into your calculator to figure out the decimal version, you can still compare your answers. Alrighty, now second list is our angles. Let me change over to red for our angles. So angle PRS. Well, following the letters PR to S, that means I'm looking at this piece down here. So that's a portion of my corner angle, but how is that corner angle getting cut up? In half. So what's half of a right angle? 45 degrees. And in fact, all of these are all going to be either 45 degrees or 90 because those are the only kinds of angles we have inside squares. Angle STR. Well, T is right at the center where the diagonals meet. And if the diagonals are perpendicular, then that angle will be 90 degrees. How about angle PSR? Again, follow it through. P to S to R. Corner angle, 90 degrees. And then angle QPR. So again, follow it along. QPR is actually part of a corner angle, not an entire corner angle, so he has to be 45 degrees. And everything is 45 or 90 degrees if you're dealing with a square. That's the only one that's divided up so perfectly like that. Alrighty, 2 more examples with squares and then we're set. Here we go. Example 5. STUV is a square with SW and WU given. So those are 2 pieces of diagonal. How do they compare to each other again? Just like in a rectangle or in a rhombus, those 2 halves of the diagonal are congruent. So we can say that 8x minus 41 equals 2x plus 13. Subtract a 2x from both sides and it leaves me with a 6x. Add a 41, let me check that on the calculator. So 13 plus 41 is going to give me 54. That divides out nicely. 54 divided by 6 is going to give us a 9. Now, rereading the question, did they want us to solve for x? No, they wanted us to solve for VT, which is an entire diagonal. Well, wait a second. SW and WU were both only half diagonals. So if I plug that into one of the expressions, what am I still going to have to do to make it work? Yeah, I got to multiply it by 2. So I'm just going to pick one of them. Let's pick SW. Why not? So I'm going to have to do 2 times SW to make segment VT. So 2 times 2x plus 13. And I'm going to go ahead and plug in my 9 as well. So that means 2 times 9 plus 13. And then just start simplifying inside out. Do our 2 times 19 first, or 18. And then do the 18 plus 3. So 18 plus, 13, which gives us a 31. And 2 times 31 gives us 62. So that is segment VT. Alrighty, last example. If FGHI is a square, solve for x. So 7x plus 3 is pointing to just the top portion of the angle, which means what is that angle measure supposed to be? Don't forget all of your vertex angles. The full angle is 90 degrees, but it is cut in half. So that means that 7x plus 3 is equal to 45 degrees, just like the bigger example 4 that we did. So then just solve for x. We don't have to plug back in for this one. So subtract a 3 from both sides gives me 42. And that means 42 divided by 7 gives me 6. So x equals 6. As always, let's see, let me know if you have any questions whatsoever. Since this is a shorter lesson, you do have both a practice and a lesson check. However, your lesson check is going to look at both of the last 2 lessons. So it'll have everything from parallelograms, squares, rectangles, and rhombi included. Let me know if you have any questions.